Okay, great. Our next talk is an invited talk. Rob Jeffries joins us from Keele University, and he's going to talk about recent developments on the formation and evolution of young low-mass stars. So please, thank you.
Okay, thank you very much. Well, young open clusters are a staple of the Cool Stars conference series. They have a long and distinguished history. Their obvious advantages are that they provide large, nearly co-evolutionary samples of stars, which are at least nearly chemically homogeneous. And these properties, of course, lend themselves to testing of stellar evolutionary models and to study the age and mass-dependent phenomena that will happen in the lives of stars. Now, thank you very much for the conference organizers for giving me this opportunity to talk about open clusters. Of course, it's an unenviable task to try and summarize the entire progress in the field of open clusters in a 25-minute talk. And so, well, I won't actually be trying to do that. So I'm going to be restricting myself to topics that surround the changes that have occurred in ideas about the early evolution of young low-mass stars, and also developments that have taken place in looking at the formation of those open clusters. And I hope to leave myself some time to at least show you some of the early results that have come out of Gaia DR2. Okay, so most of these developments have been driven by an onslaught of new data that's come in the last 2 years. I mean, I know everybody sort of thinks that they live in interesting times, but I think in this case it really is true. I can't remember a gap between two Cool Stars conferences in the past where so much stuff has actually come online. And most of what I'll be talking about will be from these particular 5 surveys, which have targeted a number of open clusters. And I should say that probably each of these could have deserved an invited review of their own on what they've contributed to open clusters. Now, I'll start off with a color magnitude diagram. So I'm sure you're familiar with these kinds of things. This is an open color magnitude diagram for a particular young open cluster, the Gamma Vel cluster. The dashed lines show the situation as it was in 1998 and for most of the last decade, which is that the models did not match the data very well at all, actually, but nevertheless, many people would have used these models to estimate the ages of these clusters and also the masses of the stars which belong to them. You know who you are, you're out there. People did actually use these models for that purpose. Now, there have, of course, been major revisions, particularly in the stellar atmosphere models at low masses. And the situation is much better now. So the red lines are the current 2015 version of the BRAF models. And, well, they match the data pretty well, and you might have some confidence that they are actually going to give you ages and masses that you might believe. Of course, there are hidden things there. For a start, I mean, you have the flexibility to choose what age that your cluster is. You can actually choose an isochrone which matches. Plus, there's no information about the masses on there. I mean, you don't know that the masses that are along those isochrones are actually the masses of the stars that you're observing. And there are still problems. I mean, we know when we look at a young cluster here, a ZAMS cluster, that the models, in fact, don't match still in detail the track of low-mass stars. And there is really no adjustment to the age that you can feasibly provide here that would lead to a good match between those the data and those models. Another problem is that even in the Hertzsprung-Russell diagram, so this isn't just a problem with the atmospheres here. Invariably, when you plot young stars on a Hertzsprung-Russell diagram from a cluster, you get this drift in ages across the isochrones. So you invariably find that the ages you deduce for the high-mass stars are actually older than the ages that you deduce for the low-mass stars. And we generally don't think this is real. We don't think that the high-mass stars all formed earlier than the low-mass stars. So this is a problem. We've also seen, well, we've seen this problem or a diagram like this a number of times at this conference. So the components of eclipsing short period low mass binaries are inflated at a given mass, typically by between 5 and 15%. And, well, this has led to the idea that perhaps magnetic fields or star spots lead to the inflation of these stars with respect to the models. Recent observations of eclipsing binaries in clusters have reinforced this view. So we can measure the masses of these stars. We think that we know their ages, but when we plot them on the Hertzsprung-Russell diagram, we find that the models simply don't match. So the positions in the HR diagram are inconsistent with where the models say that they ought to be for stars of that mass. Another thing which, well, probably the first Cool Stars conference I came to in 1991, probably, this problem was presented, the fact that K stars in the Pleiades have a spread in lithium abundances at a given effective temperature. This is not predicted by standard models of lithium depletion. This spread, we now see very clearly, is intimately connected with the rotation of those stars. So fast rotators appear to have preserved their lithium compared to the standard model predictions, whereas slow rotators have depleted roughly the right amount of lithium. This is now, it's gone beyond a vague correlation. So this is some new data in the cluster M35 where the rotation periods come from K2. And we're selecting stars from within this region here and plotting how the sort of change in equivalent width of the lithium 6708 line with respect to a mean trend varies with rotation period on the x-axis here. And you can see there's this beautiful relationship here with very few exceptions that says that slow rotators seem to have depleted more lithium, or to put it the other way around, fast rotators appear to have preserved their lithium against the depletion mechanisms. This process seems to have begun already, even at an age of 5 million years. So even right when stars begin to deplete their lithium, when the bases of their convection zones reach the lithium burning temperature, already there seems to be some difference between the behavior of fast and slow rotators. So this is work by Jerome Bouvier et al. From the Guy-Risso survey that shows that this relationship between lithium depletion and rotation is already in there with a smaller dispersion, at least at ages of 5 million years. So what's going on? Well, what's become an idea that has kind of developed now over the last few years is that we know that these young stars are magnetically active. We know that they have star spots. So maybe this magnetic activity is in some way changing the evolution of the stars compared to what the models, the standard models without these magnetic effects in, would predict. And there are two basic flavors of this idea. One is that convection is inhibited by the magnetic fields in a region below the photosphere, and the other is that star spots on the surface actually block the convective flux outwards. And both of these things will slow down the pre-main sequence evolution, leading to larger radii and cooler stars at a given age and mass. This idea has been developed by, or followed through by Garrett Summers and Mark Pinsonneau to try and explain the spread in lithium depletion that is seen in the Pleiades and other young clusters. So the idea is that if you have a star that's got lots of spots, maybe a fast rotating star, then its interior temperature, its radii, the radius is inflated, perhaps by 10% if spots block 30% of the flux from the star. And that leads to lower internal temperatures and a slower rate of lithium depletion, whereas stars with no spots, well, they behave pretty much as normal stars and have higher internal temperatures and deplete more lithium. So this is, this is a very sort of plausible way of looking at things. If we look at eclipsing binaries, then this idea has attractions as well. It has its advantages. We see, so here, this is where our standard models say that a star of this mass should be. But if we inflate that star or those stars by 10%, then indeed what happens is rather than the luminosity and temperature that they have here, the objects become slightly less luminous, but also a lot cooler, 7% cooler, and they basically match the positions that are observed for these stars. Now, is there any evidence? Well, it's a rhetorical question, really. Is there any evidence for magnetic fields and star spots on these young stars? Well, of course there is, right? That's the whole point of the Cool Stars series. So this is a plot from a few years ago now by Ansgar Reiners and collaborators, which shows magnetic flux measured using the Zeeman effect versus Rossby number, the ratio of period to convective turnover time. So this is a very familiar plot to many of you, which shows how the magnetic flux increases as the rotation rate increases, and then there's this saturation of magnetic activity at small Rossby numbers. And the fields here are 2 to 3 kilogauss averaged over the surface. So this is indeed the sort of sizes of effect that are put into these magnetic inhibition of convection models, showing that indeed this is it's a plausible thing to consider. On the spot side, well, of course we know that stars are spotted. That's how we're measuring the rotation periods, right? But we have a lot more information now about the nature of those spots. We had a whole session on this yesterday. So one thing you can do is you can fit the spectra of stars with, rather than a single temperature, you can fit 2 temperature models to try and estimate how much of the star's surface is covered by spots and what the contrast is between spot and immaculate photosphere. And this has been done for a large number of stars in the Pleiades and the Praesepe and Hyades clusters using Lamoste spectra. So the Lamoste survey looked at these clusters, and you can use particular features in the spectrum, like the titanium oxide bands, to try and estimate just how much spot coverage there is. And the answers, well, it might be quite startling to some of you, actually, that the amount of flux that's been blocked by spots at the surface of some of these stars is, between 10 and 40% of the flux is being blocked. And now this must have a very significant effect on the evolution of the star. There is a vague correlation with Rossby number. I would say it's not a great correlation. This is probably because the amount of spot coverage on these stars is highly variable. But what matters for the effects of spots on the evolution of the star is not what the instantaneous spot coverage is, it's what the history of that spot coverage was over the last thermal timescale of the star, right? So if you took the spots off a star today, it would still take a thermal timescale to actually adjust its structure to the removal of those spots. Okay, but is there any evidence that stars are actually inflated, right? This is all very indirect. So what we've tried to do is measure this inflation by multiplying together the periods and the projected rotation velocities of the stars to get a projected radius. Now, if you do this for large numbers of stars, you can model that r sine I distribution to actually try and get a true radius. And this is what we've done for groups of stars in the Pleiades, and what we find is that those stars are inflated by, on average, about 14%. So these are late K and M dwarfs in the Pleiades. They are 14% bigger than is suggested by the standard evolutionary models. And if you put that kind of inflation into your model and see what happens on the color magnitude diagram, you find that it actually corrects that discrepancy that I showed you on about my third slide. It actually moves these models onto the trend of stars in the color magnitude diagram because the stars are getting cooler at their surfaces. Other direct evidence for inflation comes from simply estimating the luminosities and temperatures of stars from spectral energy distributions and then dividing the luminosity by temperature to the power of 4 to get the radius. This has been done by Summers and Stassen, and there is indeed an increase, an inflation of radius, which appears to correlate roughly, at least, with rotation period, as you might expect. And there's a poster that you can see outside by Sam Morrell, where this has now been done for large samples of stars. And you do indeed see a small inflation at the level of 10% with respect to the standard models. Let me sort of put this together now. So this is that young cluster Gamma Velorum, which I showed to start with. This is the color magnitude diagram. This is the lithium depletion pattern of that cluster. You can get a nice 7.5 million year isochrone to run through your data. These are standard evolutionary models. And that looks like a great fit. But you see that the same models at 7.5 million years utterly fail to reproduce the lithium depletion pattern in this cluster. The lithium depletion is far greater than you would expect, and it also occurs at much cooler temperatures. If you inflate your stars by just 10%, what you find is that you can still get a great match to the color magnitude diagram, but your cluster has to be much older. It has to be more than a factor of 2 older. If you do that, you find that simultaneously you can match the lithium depletion pattern. So this is great. You can at the expense of doubling your ages, you can actually get simultaneous fits to multiple constraints on these stars. So the message is that pre-main sequence stars may be much older than you thought they were, but they also might be more massive. So this is, of course, extremely important if you're interested in cluster formation timescales, the timescales for the dispersion of disks, the timescale for the formation of exoplanets, for example. All of these things are keyed into these age scales for young pre-main sequence stars in clusters. So if those ages are wrong by factors of 2, then so are your disk dispersal timescales, etc. Right, I'd now like to move on to the sort of ages and formation of young stellar clusters. This is, well, an old plot now, I suppose. This is the Orion Nebula cluster, the Hertzsprung-Russell diagram, showing lots of stars here, low-mass stars, and showing a wide dispersion in the Hertzsprung-Russell diagram. And you could, of course, interpret this as a dispersion in ages. There are many complications to that, which I list here, right? So variable extinction, the fact that some stars are accreting, lots of variability going on. Some stars are binaries, of course. So there's been an ongoing debate, a long debate, actually, about to what extent this very broad age spread here is actually a real age spread, okay? So 0.4 of an order of magnitude here we're talking about that this would imply. I think this is, I've no time to go through all the details of that argument, but I think this has now been to some extent settled. There is approaching a consensus on this, that there is at least some age spread inside these young clusters. It probably amounts to no more than a few million years, although bear in mind that's on the old age scale. If all these age scales are doubled, then so is that dispersion. And interestingly, so the people who have been doing these Sphinx and Mystic surveys have found age gradients in many clusters. So we find that the youngest stars are actually found in the middle of these newly formed clusters. And there's a very startling result that came out in 2017 by Giacomo Beccari and collaborators, which seemed to show that a very detailed and precise color magnitude diagram for the Orion Nebula cluster showed clear evidence for multiple populations, so perhaps 2 or even 3 epochs of star formation over a few million years contributing to this cluster, with, again, the youngest population concentrated in the middle, with older populations on the outside. Now, whether those multiple populations represent epochs of star formation, or perhaps the merger of 2 or 3 subclusters, is still unknown. But that leads me to think about the dynamics of clusters. And of course, this is where the surveys like JES and Apogee have been very active in actually measuring very precise radial velocities, because The internal dynamics of these clusters are going to be, the dispersions are going to be very small. So a typical sort of virialized velocity dispersion might be of order a kilometer a second or so in these clusters. So you need velocities which are much more precise than that in able to disentangle what's going on. And these surveys have provided those kinds of precisions. So this is an example, a typical example, really, the Chameleon-1 cluster. There are actually two, spatially, you can see that there might be two subgroups here. Those two subgroups have slightly different mean velocities. They differ by a kilometer a second or so. You can resolve that. Interestingly, the velocity dispersion of the stars is bigger than the velocity dispersion of the gas and the cores in this region. And an interpretation of this is that the stars formed a little earlier. They collapsed into the gravitational potential, and then their dispersion got inflated by encounters, stellar encounters, and subsequently expanded. Now, one problem with this one-dimensional data is that you cannot tell when you look at this velocity dispersion whether this is just a genuine velocity, a dispersion of stellar velocities, or whether this is actually an expansion along the line of sight, which might contribute to the width of that velocity dispersion. So you can, well, that brings me now to DR2, because Gaia is the thing to give you that multiple dimensionality of information. The tangential velocities of Gaia are highly suitable for finding or probing the velocity structure inside clusters at distances up to perhaps a kiloparsec away or even more. Similarly, for distances, the parallaxes, the typical sort of parallax area you get from Gaia DR2 is capable of resolving clusters front to back within a few hundred parsecs. So we also get unprecedented numbers of stars in our samples, right? Gaia is basically observing everything. So, you know, you're going to be able to look at cluster distances, cluster membership, and cluster dynamics using these data. And really, so you should think of it, you can go from positions, well, we were doing that sort of decades ago, and this is sort of two-dimensional star formation studies. If you add proper motions, you go to 4 dimensions. If you add the parallaxes, you get 5 dimensions. If you add the radial velocities, you get 6 dimensions. And then if you can actually say something about the ages of those populations, you have your 7th dimension. So potentially we're doing astrophysics in 7 dimensions here. And I'll back up that claim in a second. So firstly, let's have a look at just some 2D cluster kinematics. This example was shown yesterday. I really like this example. This is an example of a cluster which is expanding, right? So the idea is that there was a supernova in Lambda Ori some millions of years ago, and that drove out all the gas and unbound the cluster. And you now see this beautiful radial expansion pattern within this cluster. Kuhn et al. Have done a survey of a lot of their star-forming regions, what you might call proto-clusters in DR2. What they find is great diversity, actually. So some of these clusters are expanding. Some of them, like the ONC, apparently are not. And what you find is that the clusters with good evidence for expansion are also have high velocity dispersions and are unbound, but other clusters like the ONC may well be on their way to at least forming fairly long-lived bound clusters. And I'm going to finish off, well, let me just say something about this. So we saw some of this in the session on Monday, but let me just point out that also what we find with Gaia DR2 is it's very unlikely that we're going to form large clusters by the merger of the subclusters that we see today. So any merging that has contributed to the formation of clusters probably happens in the embedded phase before we're actually observing them with Gaia. So once they've formed these sort of large associations, we don't, you know, there's a lot of kinematic substructure here. These probably did not expand from a single monolithic cluster, and neither are they on their way to forming anything larger. So let me leave you with an example of 7D astrophysics, as I claimed. So this is the Gamma-Vel cluster again. So this is the Gaia ESO survey view of this cluster. And you see that there are, well, the first thing that I want you to notice is that there are actually two velocity components in here. There are two, at least two, radial velocity components. One very narrow and one much broader, slightly offset by about 2 kilometers a second. Now, this is all you can see when you look at this thing one-dimensionally with radial velocities. So you would say, well, there's a very narrow component here. This may be a bound cluster, and it's surrounded by, or is at least in the same line of sight as, a much broader component, which is probably unbound. We'll call this one Group A, the narrow one, and we'll call Group B the broad one. Now, when we look at this with Gaia, we see an exceptional amount of detail here. So, this is Group A in parallax versus radial velocity. And you see that these things, these two groups, Group A and Group B, are completely separated in parallax. They're about 40 parsecs apart. Group B is 40 parsecs in the background to Group A. Furthermore, Group B is expanding. You see this correlation between radial velocity and parallax, so that the stars that are further away are actually moving away faster. So the whole thing is elongating along the line of sight. And if you actually go back 20 million years, which is what I'm claiming the age of the cluster is, you actually see that all this would come together. This thing would all come together. So these things plausibly started off in the same place at roughly the same time. They're also separated in proper motion as well, clearly separated in proper motion. So although these two groups are, if we go back in time, are compacting and coming together, they're also shearing with respect to each other. So in fact, these groups would not be in the same place at the same time, but because we've only surveyed here a fairly narrow region around the star Gamma Velorum, it's quite probable that Group B is much more widely spread over this association. And of course, that's work yet to be done. The seventh dimension is age. Here we've got the color magnitude diagram featuring these two groups. And all I invite you to notice is that when we plot the absolute color magnitude diagram, taking account of their different distances, these two populations lie almost exactly on top of each other. So not only were they roughly in the same place at the same time, that's also backed up by the fact that the two populations seem to have the same age to within 1 million years or so. Okay, so I'm going to stop there and leave you with my conclusions. So I've presented some evidence that current evolutionary models fail to reproduce a number of observational properties for low-mass stars in young clusters. Most of these problems actually could be solved by the hypothesis, I'm being careful there, the hypothesis that they are inflated possibly by magnetic fields in their interiors or star spots on their surface. There's some direct evidence that that's happening, but much more needs to be done in that area. There is, in fact, little clear evidence that it is the most rapidly rotating stars that are the most inflated, and it would be very good to try and make that connection. Turning to the properties of clusters, it now seems accepted that there is some modest spread of ages within clusters, and in some there is an isolated example of possible multiple epochs of star formation. There is evidence that some clusters are expanding and probably will not become bound clusters in the future. There is also evidence for clusters which are not expanding, and they are candidates to become the large clusters that we see at older ages. Gaia DR2 is going to absolutely revolutionize this field. There's no doubt about that whatsoever. But what I hope to have shown you, certainly with that last example, is that you get maximum leverage when you also have spectroscopy to accompany that Gaia DR2 data, because that enables you to go to what I've called 7D astrophysics. And I'll stop there. Thank you very much.
Great. Thank you so much, Rob. We have time for, a few questions, and there are a lot of questions out here. So I see someone in the back there, right there.
Marina Kunkel, Western Washington University. I was wondering, so you were testing primarily BRAF isochrones. Are there any other isochrones that you have found worked better than the others?
That's a great question. So one thing I omitted to mention, which I should have mentioned, is that actually most of the, shall we call them the modern isochrones, the Dartmouth models, PISA models, whatever, they actually agree quite well in the Hertzsprung-Russell diagram, actually. The predictions, the evolutionary predictions have converged quite closely, actually, in the last few years. So there isn't a great deal of difference, actually. The exception to that would be the so-called Parsec 1.2s isochrones. And the reason that they're different is because they have been tuned artificially to actually match the color magnitude diagrams. So the boundary conditions in those models has been changed.
Okay, I see Chris right here. Or there are two Chris's, sorry. We'll start with the first person.
Chris Tinney, UNSW Sydney. The data from Gamma Velorum is extraordinary. Are you seeing, would it be consistent with basically seeing two clumps of gas that have interacted with each other, triggered star formation, but retained the initial dynamics and so then moved apart?
I would have to think quite hard about testing that hypothesis, but yeah, on the face of it, yeah, something like that does seem to be possible. Yeah, I'd have to really think quite hard about that.
So Chris Johns Kroll right there.
Chris Johns Kroll, Rice University. So I'm wondering, wonderful talk. I'm wondering if this magnetic effect on the pre-main sequence can explain, for example, the difference in age between the low mass stars and the high mass stars for, say, upper SCO, and if so, does that require that the higher mass stars have no magnetic fields, or are the magnetic fields just not important for them?
Well, firstly, so the first part of the question is the answer is yes, and Greg Faden basically made, and others have made exactly that suggestion, that you can, if you use magnetic models to estimate the ages of low mass stars, you get an older answer, and that actually matches the Hertzsprung-Russell diagram ages for the higher mass stars quite well. The higher mass stars, of course, don't have big convection zones, and so yeah, they're less magnetic, and the effects of magnetism are less in those stars. Yeah.
Time for a couple more questions, right here, and then.
Thanawut Thanathibadi, University of Michigan. I'm just wondering, for a lot of these low-mass pre-main sequence stars, they rotate really fast. How non-spherical are these stars, and would that affect the measurement of the radius?
Yeah, that's also a good question. So some of these stars do rotate fast, but they're still a long way from breakup speed. So the effects of non-sphericity are at the 1 or 2% level, even in the fastest rotating stars. So I don't think it's not a big factor.
Question back there.
Serena Kim from University of Arizona. So when we have all the data, 60 plus spectra that we are working on, for instance, we know the temperature, for instance, and then do you suggest when we calculate the luminosity, take the 10% inflation into account and give the age, possible age range between 0 and 10%?
Right. When you say we know the temperature, what do you mean by that?
All right. Suppose,
sorry, if I can. I'm not supposed to be asking the questions.
Suppose we get good spectra, optical or infrared spectra, and then we can estimate veiling for young stars, and then we know the extinction. Suppose we get the best fit spectrum as we could from temperature. So that is we don't know what fraction of those stars would have spots on the surface. So we don't know the filling factor for the spots for individual stars. But on overall, statistically, what would be the best approach for us to actually best estimate age and give the right age uncertainty?
I would say at the moment, well, okay, so, I mean, I've tried to present it in a fairly neutral way, but I mean, I'm obviously of the view that there is something clearly wrong with the standard evolutionary models and that one should be taking into account some sort of inflation. So I would say the best approach at the moment would be to use one of the sets of models that takes into account magnetic effects. So Greg Faden's models, Garrett Summers has some models which have star spots on. Essentially, they both can reproduce this inflation, and they are likely to give better ages, in my opinion.
So there are a lot of interesting questions about your talk, Rob. They're going to just have to mob you at lunch because we have to move on. Let's thank Rob again for this fantastic talk.